What's up, YouTube? I think that we should be live any second now. What's going on? Hello, welcome to my practice stream, everybody. My name is John. If it's your first time here, the idea here is that I am just going to share my practice sessions, relearning mathematics. Why should you listen to me? I don't know, dude. I'm not a professional mathematician at all. I did study pure mathematics, but it was like more than 15 years ago. I wanted to become a professor. I wanted to go to grad school, all of that. But then I decided, no, I should go make some money first. And I went into software and stuff. Now I am rebuilding my passion for math, not so much to get into academia and become a professor, but just because I freaking love it. And I like sharing my practice sessions here on YouTube. So let's go. Here is day whatever, practicing linear algebra. We're working out of this book, and I just want to solve every single problem in this book, slowly but iteratively. So we reset last time that we streamed, we reset and started over again at chapter 1. Now we're going to work through chapter 2. Where is it? I mean, it's amazing to me. We have 155 pages already in this iPad. Recently I talked about my prestiging system here. So we got all the way to the end of chapter 5 recently, and now we're restarting at chapter 1. Once we get through chapter 6, then we'll reset and do 1 through 6. Then we'll do 1 through 7, then 1 through 8, then 1 through 9, then 1 through 10. Once we do that, then we're going to start another subject or another book in linear algebra. We'll figure it out, but we'll start another subject at that point. So let's go. Let's review. So now we are in chapter 2. Chapter 2 is about dimension, rank, and linear transformations. Here is the first problem. And I'm already somewhat stuck because I am not reading. My method right now is I am deliberately not reading the section until I need to. And I don't know what this technique is that it's referring to, but what it's asking about is let's find a basis for this subspace. So we're in two-dimensional space, which is the plane, xy. So two-dimensional space. And these two vectors, I can tell immediately that they are linearly independent. So negative 3, 1 is going to be something like this. And then 6, 4 is going to be something like this. These do not lie on the same line. They don't lie on the same line. There's a rotation from one vector to the other. So if we call these V and W, W is not equal to any multiple, a scalar multiple of V. Therefore, linearly independent in R2. And since they're linearly independent, then a basis for the span is going to be the set E1, E2. For sure, I think I know for sure a basis for this span, if we call this V and W, then the span of V and W is equal to the span of the basis vectors E1, E2, where E1 is a standard basis vector 1, 0, and E2 is the standard basis vector 0, 1. So this is, I can see that immediately based on the fact that I know that they're linearly independent. Then they will be spanned by these two basis vectors. But how else can I figure this out? In a more complicated example, I think what we would do is we would write these as column vectors. So what I want to do right now is even though I got the right answer right here, I'm confident about that's the answer. I want to see if I can come up with the idea of what that example is. What I think this is that if you take any vector in the span TUVW, I don't know, you take the vector u in the span of v and w, then u is equal to some multiple of v plus some multiple of w. So where a and b are both real numbers, right? Then this is like a times this vector v, which is -3, 1, plus b times this column, or this other vector, 6, 4. And that is -3a plus 6b and a plus 4b. And if you think about it, that is exactly -3, 1, 6, 4 times a column vector AB, and we would be solving the equation of this equals u1, u2. Okay? So then, therefore, if we're solving this equation, -3, 1, 6, 4, ... and on the right-hand side, u1, u2, then what we can do is a series of elementary row operations until we get this thing into... We will see that this is 1, 0, 0, 1, and whatever. This would be something and something else. I don't know. Alpha and beta. I mean, we don't have a specific u that we're trying to... We don't have a specific vector that we're trying to express as a combination of the two. But the important thing is that if we were to solve this equation, we would do row operations and then end up with the identity on the left, and then we would have alpha and beta on the right-hand side. That feels like a little squishy, a little unclear to me, but this is the method in general for solving a system of linear equations, right? So then what we're looking for here is reduce row echelon form, and then find which columns have pivot entries. And then the columns with pivot entries, we would then take those corresponding columns from the original matrix, like this and this. Is that accurate? I mean, can I just say that it would be the first and second entries here? let's see. To find a basis for the subspace spanned by the given vectors. I mean, a basis for the subspace could be the original vectors, -3, 1, and 6, 4. So this is like the cleanest answer that I can tell, because V is not equal to KW for any K, then here is a basis for this subspace. But if it's another problem, we could find those pivot entries and then take the columns, the corresponding columns from the original matrix. So if we are using this technique from what I expect to see in example 2, we would do those row operations, and then because these columns have in the reduced row echelon form of the matrix, or even in row echelon form, we would then find the corresponding columns from the original matrix would create a basis for the subspace. So here I had this like ... I was hand waving there. Let's actually see this row operations. -3, 1, and 6, 4, right? -3, 1, 6, 4. If we do row operations until we get to row echelon form, that'll tell us the pivot entries. We can find the rank of this matrix, which is the number of pivots in row echelon form or reduced row echelon form. So, well, I could multiply this by -1/3, the first row, and then I could subtract this new row from the second row, or take the second row minus this new row. So 1 minus 1, 4 minus -2 is 6. Then therefore, now this is in row echelon form, and it has 2 pivots. 2 pivots. Therefore, the spanned by corresponding column vectors, I'll say spanned by the corresponding columns of the original matrix. So, because this is a pivot in the first entry, this is the original column vector in the original matrix, and then because 6 is a pivot, well, let's just use yellow, why not? Then 6, 4 is also, like, these two columns form a basis for this subspace. All right, I'm pretty confident that that's what exercise of example 2 is going to be, but let's see. Let me see. What is example 2 here? Example 2. Let's write it out. Example 2 of Frale 2.1. It says, find a basis for the subspace W of R2 of R5. What am I talking about? Of R5 spanned by W1 equals 1, negative 1, 0, 2, 1. Oh my goodness. All right, W2 is a vector. W3 is a 5 vector. W4 is another 5 vector. And W5 is another 5 vector. And it says solution we reduce the matrix that has Wj as the jth column vector. So this is exactly what I predicted. This is exactly what I expected it to be. So then they have an example where W1 is in the first column, W2 is in the second column, W3 in the third, W4, W5, W6. I should have used a ... and then we reduce exactly to... they reduce all the way to reduced row echelon form. But they say of the row echelon form. They do exactly what I thought. So I got this right. I thought exactly that this is what this would end up being. So this example. So if anybody wants to work this problem for yourself, I'm just going to give you the beginning and the end. And you can work this yourself and try it for yourself. And you can avoid peeking at this if you want to. 0, 1, 1. So this is like one of those more non-trivial examples that I was thinking of. So try it out for yourself if anybody wants to, and I can give you these vectors to complete it. But I got the right idea. That's the important thing, and I'm about ready to move on. 2, 1, negative 2, 0, 0. 2, 1, negative 2, 0, 0. 0, negative 3, 2, 4, 2. 2, 4, 2. What's up, y'all? I see we got a few viewers right now. Any math geeks out there? Anybody else a math geek, dude? 3, 3, negative 4, negative 2, negative 1. Negative 4, negative 2, negative 1. 2, 4, 1, 0, 1. 2, 4, 1, 0, 1. All right, so try this for yourself. Write out the matrix with these as column vectors. You'll end up getting this thing as a row echelon form. And then therefore the vectors W1, W2, and W4. Fives? Wait, what the hell? Oh, there's 6 vectors. What am I talking? Oh, I see. W6. So we know immediately that because there's 6 vectors in 5-dimensional space, that they can't all be linearly independent. Yeah, so there's 6. 5, 7, negative 3, negative 2, 0. So then W1, W2, W5 would form a basis. The span of these is equal to the span of W1 up to W6. These both span the same space. This is a smaller basis A basis is a set of vectors that are linearly independent, that span another subspace. I think that that's an accurate statement. Let's move on. I'm going to go ahead. I got it right. I guessed at what that example was going to be. Heck yeah, getting better and better at linear algebra. Look at that. Number 7, done. Cross it out in pen. Never do it again. 2.2, let's move on to the rank of a matrix. So I already defined, or I already said the rank of a matrix is the number of linearly independent columns of that matrix. Or the number, you can compute it by the number of non-zero, or the number of pivots in row echelon form of a matrix. So this is Frale 2.2.6. And this is on the rank of a matrix. My cat is being very cute. She's cuddling with me right now. 2.2.6 says A, find the rank of the matrix. B, find a basis for the row space of the matrix. Part C, find a basis for the column space of the matrix. And D, find a basis for the null space given by this matrix. So, let's do these one at a time. For part A, and all of this is where A, the matrix A, 0, 2, 3, 1, negative 4, 4, 1, negative 4, 4, 1, 4, 3, 3, 2, 0, 3, 3, 2, 0, negative 4, 0, 1, 2. Cool. So now, again, we're going to do row operations until we get to row echelon form. And we only need to get to row echelon form. We don't have to reduce all the way to reduced row echelon form. I want to say row echelon form of A, but this is not a function because row echelon form has multiple row echelon forms for a matrix. There's a unique reduced row echelon form. But by abuse of notation, let's just write that, even though I wanted to state that that's not accurate. That's okay. We don't have to be accurate. We're just mere hobbyists over here. Okay, let's do... I don't know. Let's put the third row... What do we want to do here? I'm going to move the second row. I'm going to swap the first and second rows. And I'm going to also multiply the second row by -1. So I'm kind of doing two steps at once. But that's okay in this problem. And then 3, 3, 2, 0. Then let's also add, I'm going to add row 4 plus row 1 prime. So row 1 prime being 4, -4, -1, -4, added to the fourth row of the original matrix A. So looking at those two together, we've got 4 plus -4 plus 0, and then we've got -1 plus 1, and we've got -1 or -4 plus 2. Okay. Now that looks like a quite nice. That looks like quite a nice row, if you ask me. 4, -4, -1, -4. Let's keep that one. Let's keep that one the same. And so this one is now negative row 4 divided by 2. Right? And then let's interchange and put what used to be in the second row, let's put it in the third. Or just go ahead and do row 2. Remember, row 2 is the second row of the previous matrix. This now I want to be row 2 minus row 2 prime. Row 2 prime is the entry in this current matrix that I'm writing. So then, if that makes, I hope that makes sense to people, my notation here. Then we have 0, 2 minus 2 is 0, 3 minus 0 is 3, and 1 minus 1 is 0, right? 3, 3, and I'm just going to write that this one, I'm going to put row 3 there now. So I did some swapping around and stuff. Now, here, this third row I can divide by 3, so then I can nicely clear out all of the entries above and below it. Right? 0, 2, 0, 1, 3, 3, 0, 0. And now, I'm not going to write all the individual things. Now, this one is a nice 1, 1, 0, 0. If we divide the last row by 3, and the first row, 1, -1, 0, -1, 0, 0, 1, 0, 0, 2, 0, 1. So, now in the last row, if I subtract the first row, 1 minus 1 is 0, 1 minus -1 is 2, 0 minus 0, and 0 minus -1, 0, 2, 0, 1. And hey, that's the same as row 2. So we can clear those. 0, 0, 1, 0. 1, -1. 0, -1. We're very, 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 very close. Oh, this would be now in 1, -1, 0, -1, 0, 2, 0, 1, 0, 0, 1, 0, and 0, 0, 0, 0. Boom. Now we are in row echelon form with these pivot entries. This is a row echelon form of the matrix. Yo, what's up? I just noticed the chat. I'm sorry, y'all. Did I miss you all? I I just realized that this was, that the chat was put away. Yo, what's up, Benjamin? What's up, Bloodfire? What's up, Side Hood DSA? How are you? How's it going, everybody? Let me turn on chat for a little bit of social proof here. Look at that. Look at that. I have friends hanging out with me while I do mathematics. How's it going, everybody? How's it going, Benjamin? Okay, so this is row echelon form for this matrix. So then, therefore, part A, the rank of A is 3. Part B, the row space of A can be given by the span of these row vectors in reduced row echelon, or in row echelon form. 1, -1, 0, -1, 0, 2, 0, 1, and 0, 0, 1, 0. Right? So we can take the corresponding rows of the row echelon matrix. That works. And now here's the gotcha. The column space of A is spanned by the corresponding vectors of the original matrix. So 4, 0, 3, 0, if I write them as column vectors, 4, 0, 3, 0, -4, oh wait, no, -4, 2, 3, -4. Why don't I do something really fancy? Why don't I get so fancy that it just blows all of y'all's minds? Let's get super duper fancy. Oops. Let's cut that. Put that over here. Let's even shrink it. Well, whatever. Let's shrink that. Look at that. Look how cool that is. And then the column vector in the third column. So the third column vector right here. Copy, paste, and shrink. Look at how cool that is. That's just unnecessary. So, because those are the column vectors in columns 1, 2, and 3. C1, C2, C3. Well, C1, C2, C3 are the columns of the initial matrix that corresponding to the pivot entries of the reduced row echelon form. All right, so now null space of A. What does that mean? This is the set of all vectors such that AX equals 0, right? So always a matrix times 0 is always 0. So there's always at least 0 is always in the null space of a matrix. But there are times that there are other solutions to this equation. Yo, dude, I'm sorry to hear that you're depressed. That sucks, man. Do you want to share why? What's going on with you, man? I'm doing good. I'm practicing math. I gotta go in 30 minutes, so we gotta wrap this up. We gotta get quicker about this. So, taking the initial matrix A, and if we're solving the linear equation A x equals 0, then we can do these row operations until we get to some reduced echelon form of A. And well, any multiplication and subtraction and whatnot of the right-hand side is still going to be 0 on the right-hand side, right? So then, therefore, we can use this row echelon form, which is just one row echelon form of the matrix. Oops. I'll just rewrite it. 1, -1, 0, -1. 1, -1, 0, -1. 0, 2, 0, 1. And 0, 0, 1, 0. Right? If we're solving these equations, then what this means is that we have x1 minus x2 minus x4 equals 0. We have another equation, 2x2 plus x4 equals 0. And we have x3 equals 0, right? That's what these lines of this matrix mean. Well, we have one free variable. x4 is a free variable. If we set x4 to 0, then our whole vector x is going to be the 0 vector. But we can take another value, say that x4 equals 1, then our equation becomes x1 minus x2 minus 1 equals 0, 2x2 plus 1 equals 0, and then the last equation doesn't really add much. So then from here, we simply have x2 equals -1/2, and x1 minus, substituting x2 minus 1/2 minus 1 equals 0, right? So then, therefore, x1 is 3/2. And those circled in blue mean that the null space of the matrix A is the span of, let's double all of those numbers. So I'll just write them directly first. 3/2, -1/2, because like, why can't we double these again? x3 is 0, and then x4 is 1. Oops, x4 is 1, right? And well, remember that the span is the set of all alpha v or something. Like it's the set of all linear combinations. Hey, but G Rao, I'm sorry I missed you, man. What do I think about JEE questions? I don't know any, dude. You have to share some with me. Stump me. Give me some JEE questions. I would love to try to solve some, y'all. So because this is this any multiple, like we can multiply this by any number, then we can in particular multiply by 2, and then we get a nice vector with whole numbers. So this is the span of the null space. Bro, open Black Book for JEE Advanced. Dude, you have to tell me a problem. I'm doing linear algebra, y'all. I'm not here to study JEE math. No, dude. I'm working through this book. This is my book. This is what I'm working through. But if you want to give me a problem, dude, yeah, everybody here is just always trying to get me to solve JEE problems. No, you gotta pay me, dude. Pay me, and give me a tip, $5, and I will work your problems for you all. For $5, I'll do your homework for you. You know, I'll help you cheat on your homework sets. Don't study it for some stupid exam. Yeah, I want to study this. Yeah, it's about using concepts in depth. I mean, that's great. Yeah, dude, that's excellent. I want to be going in depth for sure, man. I mean, no, JEE's not stupid. I never said that it was stupid, man. Of course not. No, I'm a former math major, man. I'm all about going in depth, of course. But I'm just saying, I got limited time on this earth. I got 1 billion heartbeats, and then I'm a goner, dude. And I've already spent a bunch of them, you know? So I just want to be solving linear algebra problems right now. Frale, let's see, 2, 3, 6. Let's see. So assume that T is a linear transformation. And it says, if T of -1, 0 is 2, 3, and T of 0, 1 is 5, 1, find T of -3, -5. So what is the definition of a linear transformation? It means that the transformation is linear. So you can do addition inside or outside. The transformation is linear in addition, and the transformation is linear in multiplication. Right? So these two are important for T to be a linear transformation. You need axiomatic truth, not a good score. Yeah, Frale is good, man. I really like Frale. We're doing linear algebra. We're doing linear transformations. Yeah. So this is the definition of a linear transformation. This is a linear transformation. So then, therefore, well, how can I get -3, -5 from these two vectors? Okay. Oh wait, no. So, if we call this, I mean, I want to call it -E1, but yeah, it's fine. I don't know. I just want to jump right to the answer. So T of -3, -5 would be equal to... Note that -3, -5 is equal to 3 times... Let's call this one X, and let's call this one Y. Right? So then it would be 3 times X plus... -5 times Y, right? Does that make sense? So 3 times X and 5 times Y. Yeah. 3X minus 5Y equals this vector, -3, -5. So then this would be equal to 3x minus 5y, and then this is 3x minus 5 minus here. Shoot. I gave you I gave you the definition of a linear transformation. I mean, I can give you more examples, but it starts to get tougher and tougher. Here, let's do this in 2 steps. Plus t of negative 5y. Right? So, because t is linear in addition. So what I used was property A right now. That we can add these 2 things. And now I'm using property 2 to say that this is 3 times tx minus 5 times ty. Right there. And we know what t of x is, and we know what t of y is. So then, I'm really running out of space, but maybe I'll write them as column vectors so it takes less space. 3 times 2, 3 minus 5 times 5, 1. Here, let's take all this and say, note that if we call this one z, then z is equal to 3x minus 5y. And now we just do our nice little arithmetic. So we got 6 minus 25 is negative 19, and 9 minus 5 is 4. Pretty confident that that's going to be the answer, but number 6 is not in the back of the book. But I'm pretty confident that I got that, at least the general idea of that problem correct. Maybe there was a typo somewhere, but who knows. That was 2.3. What time is it? 2:46. I got 15 minutes. 2.4. Let's see. Frale is a good book. I really like this book. I think it's absolutely sick. Ooh. Yeah, dude, you should absolutely pursue a degree in math. I think that math degrees are actually going to get more valuable soon because AI is taking all the easy engineering work, dude. AI is taking all the easy engineering work. So, dude, math degrees are so much harder. They require really good, they require like great creativity. A math degree also trains you in like really sharp writing, which is really important. Like really good, clear, precise writing. So a math degree like prepares you for like strong analytical skills, obviously, strong creativity skills, strong writing skills, and the type of programming and technical jobs that are going to be out there left, they're going to get mathier and mathier. Like if you want to work on AI itself or something, you have to have studied math, dude. Where can I get jobs in which field? Teaching. You can always teach. You can go into academia. You can become a professor. You can go into data science. You can go into like artificial intelligence. Like you can always, whatever software jobs are left, like dude, a math degree will be very good for somebody who's interested in technical stuff. Yeah, man. Yeah. Unfortunately, I'm running out of time and I don't think I have time for this problem, but let me write it down. I'm going to give you credit, dude. At Giansh. Dude, I'm going to try to work this problem privately on my own because this looks cool. Thank you for sharing it. Consider the parabola y squared equals 4x. let S be the focus of the parabola. Okay. So y squared equals 4x. So notice that the square term is y rather than x. So, this is like the same as 1/4 y squared equals x. This is going to be like when x is 0, y is 0. When x is 1, y is 1/4, right? When x is 2, y is 1. Yeah, you nerd sniped me already. So, this is enough for me to roughly sketch this. It's going to be like this. And then the focus of a parabola is a certain point, like right around here, and I don't remember enough about the definition of what the focus of a parabola is. I would have to look that up again, because I've already forgotten it. Let S be the focus of the parabola. A pair of tangents drawn to the parabola from the point P equals -2, 1 meet the parabola at P1 and P2. Let Q1 and Q2 be points. Yeah, this is a hard problem. Be points on the lines SP1 and SP2 respectively, such that PQ1 is perpendicular. PQ1 is perpendicular to SP1, and likewise PQ2 is perpendicular to SP2, right? Then which of the following is true or false? Dang, dude. Which of the following are true? Is or are? Is or are. So there can be multiple answers that are multiple things that are true. A, S, Q, 1, (3 square root 10) divided by 5p I don't even know if I follow. 3sq2 equals 1. Dude, I feel like this, it's hard for me to read the notation on that. Alright. Well, here's a problem for y'all. Are there there's part B, right? Like there's gotta be others as well. And your options are wrong, let me write them. Yeah, like I don't understand what you typed there, dude. But I gotta go in 5 minutes, man. So I want to wrap up my problem that I'm actually working. All right, 245. Thanks for sniping me, nerd sniping. Linear transformations of the plane. I got 5 minutes. I gotta wrap this up. Use the rotation matrix to derive trig identities for sine of theta plus phi. So and cosine of theta plus phi in terms of sine theta, sine phi, cosine theta, cosine phi. This is just like the previous problem. So let's recall really quickly that a transformation of the plane can be written as cosine theta. I'm pretty sure that this one is negative sine theta, like this, right? So this would take a vector and then rotate it to another spot. Those vectors are different lengths, so that's a problem. But like, that would take a vector and rotate it to a new vector v prime. So then if we have if we rotate twice, then if we rotate by another angle, then we would multiply these two matrices. Cosine phi, negative sine phi, sine phi, and cosine phi, multiplied by the matrix. This is just like a previous problem that I did previously, like recently. Cosine theta, negative sine theta, sine theta, cosine theta. Right? So now we multiply these matrices. And this would be the same as one larger rotation of phi plus theta. Like, this would be the same as like rotating 2 times. So if we multiply these entries, we have cosine theta, cosine phi, minus sine phi sine theta. That would be the first entry. These are going to be long. Negative sine theta, cosine phi, minus cosine theta, sine phi, etc., etc. And that this should be the same as cosine of theta plus phi And these two entries are the ones that we really care about. So just wrap that up, finish that up. Here is cosine. Here's the angle, the sum of angles formula for cosine. Do the same thing for this entry, multiplying this row and this column, and then you get the angle addition formula for sine of theta of adding two angles. Thanks everyone for watching. This was a pleasure. Thanks for hanging out with me. I gotta go. I'm meeting a coworker. So bye. I gotta go. Bye. Bye. Thanks for watching. Bye.